Okay, so this is a demo of the electric bike. Here you can see the screen, and you can see the BLDC driver. Zoom in on that. It's a couple of FETs and current sensors and stuff. So let's see if we can move on. Here you can see 6 FETs, current sensor, fuses, DC-DC converters and stuff. It's connected to the hall sensors and to the motor, and it's connected to this screen unit, which is basically supposed to be on the steering wheel. It's also connected to the throttle. This connection here is really shitty, but it'll have to do for the moment. So here is the motor, 20-inch kilowatt, 48 volts. Now I'm driving it from this power supply, just 36 volt, to show some features. So here in the screen you can see a couple of stuff. You can see here like battery status is empty because it's such a low voltage. It should be 60 volts or so. You can see the power used by the system and the total power. It's not fully calibrated for these low values, but it will be better for higher values. You can go into graph mode, and here we can see graphs of stuff. If I twist the throttle here, you can see that I've twisted the throttle. You can see power to the motor. And we can see voltage on the system, which jerks down a bit. You can see current going through to the motor. And, well, speed. If I supply the system at full voltage, which is about 70 volts, the free running speed of the system is 75 miles an hour. No, kilometers per hour. I mean kilometers per hour, not miles per hour. So now if you look at the screen, this is the latest feature I've implemented. And when the fuse blows, the voltage will spike on the system because the motor will act as a generator. So if I twist the throttle to full throttle and then release it, power will go to the power supply and increase the voltage. And yeah, you have to stop at some voltage. I've implemented a cutoff voltage, which is the highest voltage the system can handle, or a bit over. Now it's set to 40 volts just to demonstrate. So if I here go into voltage mode, you can see that the voltage is now at 35 volts and the cutoff limit is set at 40. So if I now twist the throttle and increase the... Let's change the view here so you can see everything at once. No, it's not gonna be possible basically, but... So if I first show it like this, you have the motor, and if I twist the throttle and then release it, it shuts off the PWM because the voltage gets too high. So if we look at the screen, so you can zoom here. Yeah. So let's do the same thing again. Now we're at full throttle and I release. You can see that the voltage spiked to only 39 volts. Then the system disconnected itself and let the motor just free run. So this is a safety function. So if the fuse blows, then the voltage on the system will not be so high to damage FETs and capacitors and stuff. Let's try it again. So now if I instead release the throttle very gently, you can see that it didn't cut in there because the voltage didn't go high enough. So basically some protection mechanism. It also keeps the motor in a free running state for 5 seconds if this overcurrent thing happens. So if now the motor is short-circuited, so it's very hard to rotate it. But if I go full throttle and then release, you can see it's very easy to rotate because it's at disconnected mode. But then now it's connected again, so now it's short-circuited. So it's basically a safety system. I've implemented or going to implement more systems such as under voltage and overcurrent and everything like that. So now I can demonstrate. Let's see if we want to look at the power going to the motor. Power. So if I go through the portal, it's about 50 watts or so at this voltage. Then I can remove, yeah. I will show some more stuff when I change the levels a bit, but now let's try to stress the motor a bit. So I'm putting on some gloves to brake the motor. Well, I'm going to hold it down, try to make it rotate slowly, basically. So if I now give it a bit of throttle, you can do that. I will now show you on the screen what happens when I do so. So here you have the current going to the system, the power. It's 7 watts, it's just idle power. It's not really 7 watts, but the resolution is not that great. So if I crank it up, see here. So I try to brake. So the system was using about 260 watts or so. Now it's just at 30 volts and didn't brake so hard. But if we increase the voltage to 70 volts and brake a bit harder, the motor will deliver quite some power. The gloves get rather hot when you try to brake, so it's not that nice, comfortable to brake at a kilowatt or something. Yeah, but that's how the system looks now. So I will mount that on the bike. We can zoom back. So here is the bike upside down. It's one of those folding bikes. Yeah. So that's kind of how the system looks now. So I'm going to make some mounting plates and stuff, so I can mount the system nicely. There's also a bunch of other modes in the system. You can look at travel distance. It doesn't remember it when I lose power, but 500 meters or so now. I can go into speed limit. I can change speed limit here. It's not implemented now to the system, but it will be. Home, I can see some status, like just debug values, but I can see speed. So if I give it a bit of throttle, you can see here that the values increases. And we see here power, voltage, current, battery status. You can go to speed, which is on speedometer. As I said before, the maximum speed for 75 volts is 75 kilometers per hour. But I don't want to go that fast on the bike, so I will limit it to maybe 50 or so I don't kill myself. We can also look at other things, such as power here. We can log in real time. We can also look at current going to the motor. Here you can see it in milliamps. This is, yeah, it's not really finished everything yet, but you can see here voltage. It needs to be scaled. This is in millivolts. It should be in volts. I need to just scale it and then I can show it correctly. We have to have more.